Now, which of those has more resistance, the steel or the wood? Wood, good. What if they're both steel but one's twice as long?
Doesn't matter.
The longer one or the shorter one? The longer one. If you don't believe that, take 2 straws that you get down at the sweet shop. And you blow through the straw, it's hard to blow through. There's resistance. If you take those 2 straws and put them end to end, it's even harder to get the air through. Because it's got to go through both straws. Now, what about this? I got a fat steel cylinder and a skinny one. Which one's the greater resistance? Which one's more resistance? The skinny one. The skinny one. Now again, if you got those 2 straws, put them right next to each other in your mouth and blow. It's like a great big fat straw. And it just goes right through. It's easy to get the air through that. Low resistance. Now, the formula for resistance looks like this, where this rho symbol is a constant that's different for each substance. There's a value for copper, there's a value for wood, there's a value for platinum. It tells you how hard that substance is to get charged through. Now, at MIT, they have a tokamak. That's a toroidal device that is used to heat plasma and create energy. It was called Alcator-C. And this was the device that they achieved break-even on. That they created as much energy as they had to put in. But they had to put a huge amount of energy into the device. It had these coils in the plasma. And those coils were hungry. They needed a lot of current. And so when you would bring visitors to the Alcator-C, the first thing they noticed was that there was a great big metal I-beam coming in from outside the building, right through the center of the great big hall, right into the middle of the device. That was their wire. Okay? They had to bring a lot of current in there, and so instead of using a wire like this that would melt down, they used the I-beam off of a skyscraper. And then they had plexiglass around it so that, the grad students wouldn't touch it. That sort of thing. Now, I got a question for you. Is the Earth a good conductor, yes or no, with your clicker people?
Use it?
Greg. Did he pass?
What's that?
Did he pass?
He did. He graduated with us. Okay, last call. The answer is yes. And the key word in this question is the. If you just talk about earth, as in dirt, like a bag of dirt, that's a very poor conductor. It's very hard to get current to go through a bag of dirt. But if you take a spike and you put it into the ground, into the dirt in Bozeman, and you put another spike into the dirt in Belgrade, there are so many different paths by which the current can go from Bozeman to Belgrade that essentially you have an infinite area. And that means that the Earth, because of that area, cross-section area, acts like a huge copper ball. And that's why we talk about grounding our experiment. Typically we take our experiment and we attach it, usually part of the experiment, like the negative lead of the battery, we attach to the nearest pipe, water pipe. Because that water pipe is going to go down into the ground and it's metal. And that will connect our experiment to this great big huge copper ball. And that means that the same experiment in France that's grounded to their nearest water pipe is going to be connected to the same great big copper ball. What do we know about the voltage at different places in a metal? It's the same everywhere. It's an equipotential volume. And so that means the voltage at the negative terminal of my experiment is the same as the voltage at the negative terminal of your experiment. We're comparing apples to apples. Okay?